The name of this video is Single Capacitors. In this video, we introduce the concept of capacitance for the first time in this course. And I remind you that capacitance is the first circuit element. In the beginning of this course, we wanted to understand and study in order, for example, to build an AM radio or a superconducting qubit. How do we understand the concept of capacitance? Let us begin with the simplest case possible, which is a homogeneous conducting sphere in macroscopic electrostatic equilibrium and normal conditions. This is the center of the sphere. The radius of the sphere is capital R, as always. Now, let us assume, as always, that this is a spherical coordinate system with coordinate R. And this is the origin O. And there is vacuum anywhere except for where the sphere is defined. We know that in ME conditions, if I apply a charge to the sphere, it only distributes on the other skin, on the other surface of the sphere, not in the inside of the sphere. All right. Let us do that. So what happens if I apply a charge, for example, positive, Q1 to the sphere? Well, we know that outside the sphere, the electrostatic potential, for example, associated with this sphere will be of Coulombian type. So it's as if it were this charge, if it were concentrated in the origin. And so we can write V1 at any point R in space, in this coordinate system, equal to Q1 divided by 4 pi epsilon naught small r. Now what happens when I set R to be exactly equal to capital R1? Well, in this case, the electrostatic potential V1 at capital R, which is right on the surface of this sphere, is going to be nothing but Q1 divided by 4 pi epsilon naught capital R. It's a constant. This is an equipotential surface for the sphere. Great. Now, what happens if I apply a different charge? Q2 to this sphere. Well, we know that in this case, for example, a point R equal capital R, so obviously it's not R1, it's just capital R here. Well, in this specific case, it so happens that the electrostatic potential V, let us call it 2 because it's that generated by another charge, Q2. So V2 at point capital R is going to be Q2 divided by 4 pi epsilon naught capital R. So these two potentials are obviously different. So we have a different electrostatic potential depending on the source charge that we put on the external surface of this conducting sphere. Now, what happens if I compute the ratio between, let's say, Q1 and V1? At capital R, for example. Well, the result of this ratio is very simple. We get Q1 divided by Q1 over 4 pi epsilon R. So Q1 and Q1 cancel out, where the first one perhaps is good to show it. It's Q1 divided by the potential, which is Q1 divided by 4 pi epsilon naught capital R. So obviously these two Q's cancel out, 1 over 1 over 4 pi epsilon R gives me as a result 4 pi epsilon naught capital R, which interestingly enough is exactly the same if I were to do Q2 divided by V2 at capital R. You can show by means of a similar calculation that you get exactly the same result. We get exactly this quantity. As it turns out, this quantity here, it's a constant and is a property of this system. In particular, is a property of the ratio of a given charge and the corresponding potential at a given point. And so this quantity, we call it capital C, capacitance. Okay, so this one is worth highlighting in yellow. for example, the capacitance, capital C, for a sphere, a conducting sphere, is given by 4 pi epsilon naught capital R. And as it turns out, the units in SI for this quantity, which again is called capacitance, in SI, the units are farad. Either you spell it entirely with small lowercase f or simply capital F for farad. And as it turns out, 1 farad is a huge capacitance. So typically, for example, in my lab, we deal with attofarads. So already a nanofarad is a pretty big quantity, okay? All right, so the qubits, which I've seen in one of the screencasts in the beginning, has a capacitance really of a few attofarads, so really, really small capacitances. And these are islands of a few hundred, half a millimeter by half a millimeter. So they're not that small, they're not nanometric, they're pretty visible with your eyes. And yet the capacitance is super small. So capacitance of a farad is huge. All right, so now we know this concept in this very simple scenario. Let's try to generalize it a little bit. So the generalization I want to do now is, let's not consider a conducting sphere. Let's consider something more complicated. So something, a conducting object in ME, as always, with a generic shape, whatever you want to call it. This is our object, capital gamma, for example. And so it's completely full with a conducting material in macroscopic electrostatic equilibrium. So in this case, as it turns out, let's call a point right on the surface of this object as P naught, and a point outside P, so capital P is a point in the vacuum outside, right on the surface of capital omega, which is on capital sigma, which is the skin of this object. We have a point P naught. Okay, P naught is on the surface, P is anywhere in the vacuum outside. So as it turns out, in the vacuum region outside, I can write down a fundamental equation, which for the electrostatic potential is, in vacuum, Laplace equation. So the scalar Laplacian of V at any point capital P in space has to be equal to 0 in the vacuum region outside capital gamma. Great, so we have Laplace equation. This means that the solution V at any point capital P is a harmonic function. See vector calculus. Now the fact that this is a harmonic function has an important consequence. An important property of harmonic functions is that the ratio between, for example, the electrostatic potential V due to a charge distribution 2, so that is, we apply a charge, first we apply a charge Q2, which in ME distributes only on the outer skin capital sigma. So this Q2 results in a V2 in a similar fashion as we have seen for this problem here for the sphere. So we get a V2 due to Q2, my source charge, at point capital P. Now, if instead I consider a charge Q1, this generates an electrostatic potential V1 at any point capital P. And if I do the ratio between V2 at any point capital P in vacuum, so this is a variable potential, and I derive it, I divide it by V1 at capital P in this fashion, as it turns out, this is exactly equal to the ratio of V2 at any point capital P naught on the surface capital sigma divided by V1 for any point P naught on capital sigma. Okay? And hereafter, I will skip this P naught. So whenever I do not clearly specify a variable point capital P, like here, V2 divided by V1, this represents the electrostatic potential due to a charge Q1 right on the surface capital sigma, which is an equipotential surface, so this is a constant value. And for Q1, it's the same thing, right on the surface capital sigma, this is an equipotential surface, so this V1 is a constant value, which is exactly the value at the surface when I apply a charge Q1. So these are constants. This is constant 2, and this one is a constant equipotential surfaces 1. Great. All right. So now we know that this ratio is correct. For example, you can convince yourself that this is true in the case of the sphere. So if we were to do this in the case of the sphere, what do we have? Well, we end up having Q2 divided by 4 pi epsilon naught, in this case small r, because it's the generic value here, okay, due to Q2. And if I do the ratio between this and Q1 divided by 4 pi epsilon naught and again r. In this case, this quantity clearly gives me Q2 divided by Q1. Nothing more than that. So it's a constant quantity. All right, so this is actually very nice. And for example, you can also do it to verify that this is correct, right on the surface. So if you do the ratio, Q2 divided by 4 pi epsilon naught, right, a capital R, and I divide it by Q1. This is also true. This is exactly what I'm doing here. So first I calculated this quantity here, and then I calculated this quantity here, and both give the same result. So these are constant because these are equipotential surfaces right on capital R. So these cancel out. And again, okay, Q2 divided by Q1, okay, which is an important property. All right, so to summarize this property down here, we can finally summarize this as follows. In general, the ratio between the electrostatic potential V, capital V. Let me generalize in the following fashion, actually. It's a little bit more generic. So let's do it even more general. So in this case, V2 at any point capital P is equal to V2 constant divided by V1 constant time V1 at point capital P. I'm just extrapolating from this relationship here. I find that V2 at any generic point capital P is equal to V2 over V1 times V1P. So I take all this construction here, actually to be more precise, I'm taking this construction here, this is just an example. I just reshape it a little bit and that's what I obtain. Then this quantity, which we want to circle in yellow, and this is due to the properties of harmonic functions. Okay, so let us summarize this case of single capacitors. So again, to summarize here, we have a single conductor, let's call it capital gamma, with external surface capital sigma. And suppose that we apply, of course everything is microscopic electrostatic equilibrium, the conductor is here, and all the rest is vacuum. So if we do apply a charge Q1 in microscopic electrostatic equilibrium, it will distribute on the external surface capital sigma. In this case, so we will have an electrostatic potential, let's call it V1 at a generic point capital P in space, where this point capital P is in the vacuum. So this is a generic point capital P in vacuum. If we now apply a charge Q2 to this object, this will generate an electrostatic potential V2 at point capital P. The relationship between these two electrostatic potentials, due to the fact that V is harmonic function, is going to be V2 at P equal V2, and remember that this is a summary of what we have written down here. So this V2 means right at any point on the surface capital sigma, like a point P naught, like this one. So I don't specify, it's just a constant value, divided by V1, which is a constant value. These two constant value, one is on any point P naught due to Q2 and one is due to Q1, respectively. So this is the relationship which we found before. So now the next thing we want to do really is to use Coulomb's theorem. So let us use Coulomb's theorem. And the way we want to use Coulomb's theorem is to find mathematically the value of the charge Q1 or Q2 given the electrostatic potential, which we solve by means of the Laplace equation in vacuum. So if we do that, so we're going to find that, let's do this up here. So Q1, so we know that the total charge divided by epsilon naught, because it comes from Gauss's theorem, Coulomb's theorem obviously, Q1 divided by epsilon naught is equal minus the integral, so we need to do minus epsilon naught. I'm just reshaping Coulomb's theorem a little bit. Then we need to do the limiting surface integral on the surface capital sigma plus, where I remind you the capital sigma plus is the surface approaching capital sigma from the outside. So it's this outer skin here. This is capital sigma plus in Coulomb's theorem. In Coulomb's theorem, great. So this has to be intended as a limit, of course, very important. The limit is not right on the surface. Right on the surface, of course, the potential is constant. But since we are approaching in the limit, we can still take the derivative, the directional derivative with respect to n, where n, as always, is a normal unit vector of this type, normal to the surface capital sigma. All right, of what quantity? Well, we are doing Q1, so this one is going to be V1 at any generic point capital P. Again, the fact that this is a limit is critical because if I were to calculate this derivative right at any point P naught on capital sigma, it would be 0 because V1 is constant there. In the limit, it's not. Okay? Lots of students have lots of problems with that. Again, it's a limit. So the field here and the potential are not constant. They vary in the limit. You can do this. And this, of course, has to be done dA. Similarly, we can use Coulomb's theorem to calculate, to compute the charge Q2, which is going to be equal to minus epsilon naught, again from Coulomb's theorem, the limiting integral on capital sigma plus, same as up here. And now we do the directional derivative again with respect to n, external replay problem of Q2, so it's going to be V2 at point capital PDA. But we know that V2 is given by this relationship, so this we can eventually rewrite it as minus epsilon naught integral in the limit to sigma plus from the outside of V2 over V1, which are constants, so we don't integrate over them. So these constants, eventually, we can take them outside. This kind of integral, if we want to, V1 of P dA. Okay, nice. So now let's see what we can isolate here. Okay, we can isolate all this stuff in yellow. So we bring this outside and we end up with this quantity here, which when integrated on capital sigma plus is nothing but this quantity up here. So this can be rewritten Q2. We can rewrite it eventually simply as V2 over V1, which are constant with respect to the integral, so we don't integrate them, times Q1. Okay, so by reshaping a little bit this equality, Q2 equal V2 over V1 Q1, and generalizing, so reshape, so here we reshape and generalize, I'm not going to write it down, we can write the following sequence. And the sequence will tell us that V2 over Q2 over V2, Q2 over V2. Yeah, I bring this to the other side, so that's perfect. Q2 over V2 equal to Q1 over V1. In fact, this we can generalize it to any possible charge Qn that you apply, which generates a potential Vn. Okay, so this is my generalization, reshaping a generalization here. This quantity, obviously, is always the same, so it's a constant. This we call it C, which is the capacitance for a single conductor. So for a single conductor, we obtain a single capacitor if you want. And so this C can be simply written in general as the charge Q divided by the electrostatic potential. Okay. So now, as it turns out, so this is our capacitance here. There are lots of problems with the concept of capacitance and even more so with inductance for some unknown reasons, because the concept of capacitance and inductance are effectively the same. Okay, it's the same concept. One is for the electric field, the other one is for the magnetic field. So as it turns out, for a single conductor, because of VR harmonic functions, this ratio, no matter what, is always a constant. So this constant is an intrinsic property of single conductors. There is nothing you can do about it. Interestingly, think about, you go to buy some bread at the shop, right? At the bakery. Do you question the concept of mass? I don't, because somehow we are used to the concept of mass since we are a child. And so if you write F equal ma, and I'm only writing second Newton's law without vectors, okay? So this quantity here, which is the mass, which we don't apparently seem to question too much. We don't question what is the concept of mass. Well, it's a proportionality constant between the force and the acceleration. We don't question it. It just happens that in physics, the ratio between F and A, the force and the acceleration, is the mass, which is a constant for this system. The capacitance, similarly, is a constant for the ratio between the charge, which is the source of the electrostatic field, and the electrostatic potential, which is a property of the field, if you want. It represents effectively with the scalar the electrostatic field. So it's the same kind of concept. So if you don't question this concept, you shouldn't question that either. It so happens that it's always a constant, as shown here. So it's a fundamental property. This is basically a definition, but it comes from this fundamental property. No matter what, is a constant. As it turns out, the inductance is the same kind of concept, okay? However, in that case, it's going to be a constant. The relationship is that the inductance is the ratio between the flux due to the magnetic field and the current. So in that case, we are relating the current, which is the generator, the source of the magnetic field, and the magnetic flux, which play effectively the role of charge as a source and potential. So we will see this towards the end of this course. If you understand the concept of mass, or you think you do, and you don't question it, capacitance is the same kind of concept. Inductance is the same kind of concept. So they are all constants in these systems. And then you can also say, eventually, some people say the capacitance is the circuit element where the electric field or the electric energy is stored. Yes, sure. Actually, I don't like that kind of interpretation. It's really just a constant, and this constant is given by the ratio of the charge, which generates the corresponding potential. 2 with 2, 1 with 1, and with n in general, Q over V, which again is measured in farad. In the next video, we are going to discuss about multiple capacitors, which eventually will lead to the concept of a parallel plate capacitor, and for example, a cylindrical capacitor, which is the one I use in my AM radio, and for example, also spherical capacitors, which we will encounter in some home assignments. That's it.